Hi everyone, welcome back for another video for heat and mass. So today we're going to have a pretty similar example to what we had in our last example, or in our last video, sorry. So it's going to be slightly different, but we're once again looking at a specific system that has numbers associated to everything, and we're going to plug this into our Excel sheet and see how the numbers can change depending on this specific system. So I have my paper right here, which is completely blank other than our agenda on the top. So our specific example today is going to be dealing with a catalytic surface. So we're going to have ethanol coming down from our atmosphere, reacting with this catalytic surface and emitting acetaldehyde and hydrogen. So what that essentially means is that ethanol is coming down and reacting to this catalytic surface, whatever it is, we're just defining it as catalytic surface. And then because of that reaction, it's going to now emit back up into the atmosphere the acetaldehyde and the hydrogen. And so once again, we're going to put this into Excel to solve that Maxwell-Stefan equation that we kind of looked at last time too. So we're going to begin this problem in a very similar manner as last video. And then we're also specifically looking at the reaction rate per area and kind of seeing how that changes, and then the surface mole fraction of ethanol. So we're going to know what the mole fractions are in the bulk phase at the very top when everything is mixing together, but we want to see what the surface, that catalytic surface mole fraction rate is of ethanol. And then secondly, our other agenda for this video is to show the extremes of diffusion and reaction limited operating conditions by varying that reaction rate constant that we're going to solve for using our initial conditions and kind of seeing how we have these extremes one way or the other. So yeah, we can go ahead and get started by drawing our system. So for example, I'm just going to draw our catalytic surface as just like this line down here. And once again, we have ethanol coming down. And we're going to have acetaldehyde and hydrogen coming up. I just drew these arrows as varying lengths, not due to one going up farther than the other, nothing like that. It was just so that I could write the full name out without them overlapping. But this is our system here. So we have that catalytic surface with ethanol coming down, reacting, and then emitting acetaldehyde and hydrogen back up there. And then also at this very top area here, we're going to have some sort of, should have given myself more room. We're going to have some sort of bulk phase here, which I'm just going to represent as a square. But there isn't some sort of hard cutoff for the bulk phase. It's just saying that when we're far enough away from the catalytic surface such that that has no input on the mole fractions that are in the atmosphere up here, it's far enough away that the catalytic surface will not cause any changes. That is what your bulk phase is. And that just says this is where ethanol, acetaldehyde, and hydrogen are all mixing together. So once again, I've just represented that by like a square up here, but it won't actually be some sort of hard cutoff. It's kind of just an area far enough away. But for this example, we have measurements for the distance between that catalytic surface and where the bulk phase begins. And we know that that's going to be, I'm going to represent that by delta, and that's going to be 1 millimeter, or 1 times 10 to the negative third meters. So So we just know that that distance between the catalytic surface and where the bulk phase begins is 1 millimeter, which is important to know because similarly to our example in the other video, we had that sort of volume between where the liquid mixture started and where the pure nitrogen was. It's kind of a similar thing here, but we're looking at a surface versus the bulk phase area. So we've just defined this as delta equals 1 millimeter, or 1 times 10 to the negative third meters. And then we also know our mole fractions in the bulk phase. So this is kind of giving us what our initial conditions are of sorts before we see how these mole fractions are going to change at the catalytic surface, which is kind of what we're looking at here, is seeing what this catalytic surface looks like. So we're essentially defining initial conditions here by saying what our mole fractions are in the bulk phase. So I'm just going to write that over here so that we recall that these are bulk phase mole fractions. And then I'm going to assign each of these components a number once again, like we did in the previous example. So ethanol will be 1, acetaldehyde will be 2, and hydrogen will be 3. So for the mole fraction of 1, or mole fraction of ethanol in the bulk phase, is going to be 0.6. The mole fraction of acetaldehyde is 0.2, and the mole fraction of hydrogen is 0.2 as well. So these are the mole fractions that we have in our bulk phase. I've just written that on the side here. And then we have a couple of other initial conditions that we know. We also know that the pressure of our system is 101.3 kPa, and our temperature is 548 Kelvin. So this is just for our system as a whole. We have a pressure and a temperature defined. We also know that this is a first order reaction, and so that's going to have some sort of associated reaction rate. And we are given that the reaction rate, which I'm going to represent by K subscript R, so that reaction constant rate is going to be 10, and that'll be 10, I believe it's mole meter squared per second per mole fraction. Let me double check that those units are correct. Yes, okay. So our first order reaction constant is 10 moles per meter squared per second per mole fraction, which I've just written as mole frac. We also have our mass diffusion coefficients for each of these again. So as we recall from that other video, this is something that is known, it's found experimentally, so these will remain constant depending on what components you're looking at and how they diffuse within each other. So we have that D, which is that the variable that represents that number, 1, 2, or how ethanol is going to diffuse in acetaldehyde, is going to be equal to 72 millimeters squared per second. And then we have for the diffusion coefficient for ethanol in hydrogen, or D13, is going to equal to 30 millimeters squared per second. And then lastly, we have D23, or how acetaldehyde will diffuse in hydrogen, equals 230, again, millimeters squared per second. And to get this in our regular units, we can say that this is 72 times 10 to the negative 6 meters squared per second. And then 230 times 10 to the negative 6 meters squared per second. 230 times 10 to the negative 6 meters squared per second. All right. So this is all of the initial conditions that we are given here. So we have all of this really good information, and we're going to go ahead and begin setting up our Stefan-Maxwell equation again, the way that we did for that last example, you'll recall that we had that our delta, sorry, that, not delta, that we had that curly n, which represents that like scaled position factor, is equal to delta over, or sorry, z over delta. So hopefully this sounds familiar to you. It's just saying that scaled factor is going to be a value between 0 and 1, because it's essentially saying how far along are we from that starting position until our final position, like what percentage through are we. So you do the position that you are at divided by the total length, and that gives you some sort of percentage of sorts of how far along you are. So we can also recall that dz equals d curly n times delta. So this should look pretty familiar to you. This information here, this is what we did in that other example too, in order to factor in our scaling value, or sorry, in order to factor in our delta into our Stefan-Maxwell equation. So we can begin writing our Maxwell-Stefan. I keep saying Stefan-Maxwell. You get the idea. We can begin writing those equations for both ethanol and acetaldehyde, and we don't need to write it for hydrogen because we already have information about the first and the second system. So writing about the third system is kind of redundant because we can just solve for the third one based off the first and the second. So for ethanol here, we can write that our driving force of 1, which is ethanol, that's what we've defined ethanol as being, assigned number 1, and that is the same as dy1, or equals dy1 over d curly n. And then that is equal to delta times our summation. So hopefully this sounds a bit familiar to you. This beginning here, we have the driving force of 1 is equal to our change in mole fraction of 1 over that scaling position, equals, and then you have to put that delta in to change this from dy1 over dn from dy1 over dz. That's why this is here, because you're changing this. And then we have our summation, which I'll write out again. We have yinj minus yjni all over our total concentration times dij. So hopefully that looks familiar to you as well. So we can go ahead and plug in these numbers. So we have delta times, y1 and 2. And once again, we're skipping when j equals 1 because those would cancel out and become 0. And then we have y2 and 1 for CD12 plus delta times y1 and 3 minus y3 and 1. CD13. So this is going to be what represents our, oh my gosh, dropping my notebook, sorry. This is going to be what represents our values for the driving force of ethanol here. So this is what we have when we've expanded it out a little bit. Now we can write the same thing for acetaldehyde. Which is our 2. So driving force of 2 equals dy2, d scaling factor, equals delta times y2 and 1 minus y1 and 2 CD21. And then as we recall, um, diffusion, the diffusion coefficient, mass diffusion coefficient of acetaldehyde in ethanol is the same thing as the mass diffusion coefficient of ethanol in acetaldehyde. So even though those numbers are switched, it's going to be the same value. Plus delta times Y2N3 minus Y3N2 all over total concentration times CD23. So now we have expanded out both the driving force of ethanol and acetaldehyde, which is good information for us to have written out for when we start plugging these Maxwell-Stefan equations into our Excel sheet. Now, similarly to what we did in the last video, again, we're going to come up with some sort of guess for the flux of 1. And we're going to do that using our acetaldehyde relationship that we just made. So once again, we'll recall that the dy2dn fraction is going to be essentially 1, and then all of those mole fractions, y2, y1, y2, y3, all of those are going to be essentially related to 1 as well. And so we're going to be looking at this specific example here. The N2 we'll get rid of, and the N3 we'll recall that the flux of that we're getting rid of as well. So we're going to just be looking at this N1 here. And if we rearrange this, the N1 over CD21, we can get that N1 is equal to concentration D21 all over delta. So we've just kind of simplified this piece right here with the delta in there as well. And we can also recall that total concentration is equal to pressure over RT. And that is something that we learned in that last video as well. So if that doesn't make sense how we got that, you can check that video out just to double check. So we can plug P over RT in for concentration. So it'll be PD21 over RT delta. And this is just, once again, giving us a good guess for what this flux is going to be. And then also we need another guess variable here too. So we need to make some sort of guess for what Y1 is going to be. So that's the mole fraction of ethanol. So for the mole fraction of ethanol, we're going to make a guess using our first order reaction rate. So this is a guess for what it's going to be at the catalytic surface, and the reaction rate directly relates to what that value is going to be at the catalytic surface. But once again, we're just making a guess because we can't possibly know this information yet. And then we're going to use Solver on Excel once again in order to actually solve for the actual value. But our guess for Y1 is going to relate to the flux of 1 divided by the first order reaction rate of 1. So this is represented here. So the flux of 1 divided by that first order reaction rate, which we had decided here, and then that was our plugged in guess for flux of 1. And then we're also going to just define Y1 as being 0.5, so mole fraction of 0.5. This is once again just another guess. And then we know that Y2 and Y2 is going to be 0.5. And then we know that we're just defining Y2 as being 0.5, so we have some sort of starting value once again, and then Y3 is going to be 0.5 minus Y1. or 1 minus, sorry, it's going to be 1 minus 0.5 minus y1. And so these are a couple of starting values that we're just defining. Y2, 0.5. Y3 will be 1 minus 0.5 minus y1. Okay, so now that we found all of that good information from the Maxwell-Stefan equations, we can go to Excel, which is what you're looking at now, and begin putting in all of these values that we have. So we need to start inputting all of those initial conditions that we were given once again, which is unfortunate, but it needs to be done. So delta, we recognize that that was 1 millimeter, or 1 times 10 to the negative third. And then 1 times 10 to the negative third meter. And then we have that our pressure is going to be 101.3. And this is also times 10. But this is times 10 to the third because it's kPa, so we got to make that in just pascals. And then T, sorry, I'm like not very good at going fast on Excel. 548 Kelvin, and then our concentration, I'm going to put dots after these just in case they get funky. Our concentration, we'll recall, is going to be, actually I need to put R in here first, because we need R to solve for our concentration. So R is going to be 8.314. And then our concentration, now we can solve for it. It's P divided by R times T. So there's our concentration here. And then now we can put what our bulk phase components are. So I put a little b here to represent the bulk phase, 0.6 for ethanol, Y2B 0.2 for acetaldehyde, and Y3B 0.2 for hydrogen. So these were all the values that we had been given. These are all our initial conditions, and we still have a couple more to put in. So we know that our first order reaction rate is going to be 10 once again. And then lastly, our diffusion coefficients. So for how ethanol diffuses in acetaldehyde, we had that as 72, and then this is times 10 to the negative 6 because we need it in meters squared per second instead of millimeters squared. And then D13, or how ethanol diffuses in hydrogen, is going to be 230, once again, times 10 to the negative 6, and then D23 is going to equal 230 times 10 to the negative 6 again. All right. So now we have all of these. These are all our initial conditions here. We're going to go ahead and make these all formulas so that we have, when we begin typing in the equations, we can just call these variables for these values instead of going directly to the values. And then, yeah. So now we can put in the value that we found for our guess of N1, and therefore find guesses for N2 and N3. So since this is a balanced example, so 1 mole of ethanol can come down and create 1 mole of acetaldehyde and 1 mole of hydrogen. So because these are all equal, they're all scaled the same way, so they're all going to be equal in magnitude, but the only difference is that acetaldehyde and hydrogen, aka 2 and 3, are going to be the negative version of 1 because they're diffusing the opposite way. So we can recall that when we drew our example, we had ethanol coming down, and then acetaldehyde and hydrogen coming up. So they're just going to be the negative version of 1. So we'll plug in the problem that we solved for, so we can recall that was equal to the concentration, so C dot times how 2 diffuses in 1, which is the same as how 1 diffuses in 2, divided by our delta. And that's what we get for our value here. And then down here, we can just say that's the negative version of this. And then same thing here. So now we have guesses for all of these fluxes here. And then we can also put down here what our guess was for the surface value. So that's the part that I put at the very end here where we said that, where we said that y2 was equal to 0.5, right? And then y1 was equal to the flux of 1 divided by the reaction rate. So hopefully you remember that from a second ago. So we had this equal to 0.5, this equal to flux of 1 divided by this, and then we had y3 as being equal to 1 minus this. So now we have our mole fractions for the surface, we have our flux, and then we have mole fraction in the bulk phase, plus all of those other beginning values that we needed in order to solve for those fluxes. So now we can start organizing our Excel sheet similarly to what we did in that last video. So just like last time, we're going to have this dz over here starting from 0, and then we're gonna fill this down all the way until 1000 again. Columns, blah, blah, blah. And then, where's our delta? Here it is. So this is our total length. So what we're going to need here is we're going to need to find our counter length over here too. So that's once again like the amount of steps that we have. So the total length, which is delta here, divided by the amount of steps that we have, which is 1000. So this is our counter. So each time we multiply it by the side step, that's how far we've gone total. So we do this times our counter here. I'm going to go ahead and put a little $sign so that stays the same, and then fill that down. Oh, okay, so that did not work. What? Oh, I just clicked the wrong box. There we go. Let me try that. There we go. Okay, and then just to double check, at the very bottom here we have 0.001 as our total total length, which is what we want because we know that that's what our total length is, delta here. And then here we're going to have our y1, y2, y3, and then this is going to be our bulk phase, or sorry, this is going to be our surface. So we'll have this equal to this value here. Oop. Oh wait, I need to make this an equation first. Oh gosh. I don't know why that did that. I need to make all of these equations first. I think I already did for those up there. Or make it a formula so that we can call those values directly. So y1s, because we're starting at the surface here, y2s, and then y3s. So yeah, once again, this is starting at the surface because we defined our surface as being 0.0, and then our bulk phase, the very end, being our the very top, which is at position 1 millimeter. And then now we can say this is our dy1 divided by dn, and then dy2 divided by dn. So this is our Stefan Maxwell equations here, and we can begin plugging this in. So now we have delta times, and then we're going to do y1 and 2. So y1 times n2 divided by, y1 times n2 minus y2 times n1 divided by our concentration times d12 here. Okay, and that's our first piece, and then second is delta again times y1 times n3 minus y3 times n1 divided by our concentration. Sorry, I'm looking to the side. I'm just looking at my paper here. It's times concentration D13. All right. So this is what we have for our driving force of 1, and then we'll do the same equation for y2, but slightly different numbers. So once again, we have delta times y2 times n1 minus y1 times n2 divided by concentration times D21, which is the same as D12, plus delta times y2 times n3 minus y3 times n2 divided by concentration times D23. And there's our value for that. So now we can show how this composition is changing. So we have this plus the position you're at times how it's changing. And then same thing here. Before plus the position you're at times how it's changing. And then this is still equal to 1 minus this minus this. All right. So then we can pull that down here. See these values changing, and then we can send it all the way down. Okay, so we can see how these are slowly beginning to change as we go down here like this, right? So it's continuing to change as we get up to the bulk phase, but we can recall that, what is this, 1003? Similar to what we did last time, we can recall that we know what the bulk phase compositions are, or what we know that they're supposed to be. So this is how it's changing based on our guess flux that we made in the guess molar concentration. But now that we have this set up, we can actually see what this guess is versus how it compares to what it actually is. So H1003, this is what it's saying Y2 is gonna be, but we know that it's actually supposed to be 0.2. So this is our guess, and this is actual. And then we have, this is I1003. So Y2 in the bulk phase is supposed to be 0.2. Sorry, I'm mess this up. It's supposed to be 0.6. And then this is J1003. And then that's going to be supposed to be 0.2 as well. So now we can do similarly to what we did last time, which is the actual minus our guess. And then we're going to square this because we're trying to get our error here is what we're doing. Actual minus this. And so we find that this sum, we're trying to minimize the error here. So this right here is the error that we're finding, the squared error between our actual versus what our guess was. And then we're taking the sum of that, and that's this right here. And now we're going to use solver just like we did last time in order to get this as minimal as possible. So we're trying to minimize this value. So this value here, we want to minimize it. And the thing that we're going to change is our concentration. So we need to grab these two here. So we're changing the concentration of the ethanol and the concentration of the acetaldehyde, and then because of those two changing, the hydrogen will change as well. So we don't have to include that here. And we have to make sure that these are non-negative, and then we're going to solve. Okay. So this is still pretty high, and this is also 0 here. So let me change this to be 1 minus this minus this, which is what we have here anyway. And then let me try to do solver once again, because let's see what we have down here first. So these are still not quite right. So these are not right. We still have this, yeah. So let's try solver again and see if this will fix it. So this value here, we want to be minimal, and we're going to change these two values here for that. And then let's try that one more time and see if that. So that still didn't work. Let's try to go back. Let's try to go back to our original values that we had. Oh, okay, so that's still done. So I'm just going to restore this back to our guesses again because this did not quite work. So I'm going to go ahead and change this back to N1 divided by KR, and then this being the negative version of that, this being the negative version of that. Oh wait, this is the wrong. Sorry. Yeah, sorry, Y1, that's right. But then this is 0.5. And then this is equal to 1 minus. I don't know why this is negative. Oh, I hate Excel. Okay, there we go. And then we have 1 minus this minus this. Okay. So we're back to this. This is what we want. Okay, why does this look so much different? Okay. Let me make sure that this is correct. Right, that should be good. What? Let me see what is different about this. Delta times 2 minus 1 C 1 2 plus delta. Okay, I think that should be fine. Oh my gosh, why does this keep doing this? Okay, and then this should be fine. It should all be fine. So let's go ahead and try this solver one more time. Let's see if this does any better than last time. So this still did not do good. Let's try all three of these. So this is actually our flux here, so that's why I'm getting such funky numbers, and then we'll change this back. So the N1 divided by KR again, this is equal to 0.5, and then this one was equal to 1 minus 0.5 minus this here. Okay, so now we've reset this. This looks a little bit better. Let's try to use the solver on these numbers. I think this should be correct now, but we'll give it a shot. Let's see. Okay. Okay, this looks much better. So now let's double check this down here. Perfect. So now we have 0.6, 0.2, and 0.2, which is what we wanted. Those are the actual values now. So I had messed up plugging in our fluxes, and you could see how that completely throws off the whole system. So now we have it correct. And these are the actual values that we want at our bulk. So, yes. Yeah. Wait. Okay. Yeah, I think that's correct. Okay, so that's going to be everything for this video. Hope you enjoyed.